Hi, this is a lesson on electric charge and electric fields, and also the forces that electric charges exert on other electric charges. All the images that you see in this video are attributed to OpenStax College Physics, which is a text by openstax.org, distributed under the Creative Commons Attribution License version 4.0. What is electric charge? Well, electric charge is a property of certain particles that exist in our universe. And it's interesting that there are actually two different types of electric charge. There's positive charge, which in everyday matter is carried by protons, which exist in the nuclei of atoms, and electrons, which carry negative charge and orbit the nuclei of atoms. And this is important because it turns out that charges exert forces on other charges. And if you have a collection of positive charge near a collection of negative charge, what we find is those collections of charge exert an attractive force on one another. On the other hand, if you have positive charge near positive charge or negative charge near negative charge, you'll see a repulsive force developed between those stores of charge. So the electric force, because of the fact that there's two different flavors of charge, positive and negative, can be attractive if you're dealing with opposite types of charge, or repulsive if you're dealing with the same type of charge. So because electric charge is a property of atoms and materials, matter is made out of trillions upon trillions of atoms, every object in the world around you has a tremendous amount of electric charge residing within it. But in most situations, the charge is balanced, meaning that there's just as much positive charge as there is negative charge. So the total is zero. And what we would say is that is a neutrally charged object. But it turns out that in certain situations, you can redistribute the electric charge from one object to another and create an unbalanced distribution of charge. And there are two main ways that you can accomplish this. The first way is called charging by contact, and that's what's being pictured down here. So this picture is showing in panel A, you're starting out with a chunk of amber and a cloth. And the amber is neutrally charged. It has a net charge of 0, and the cloth is neutrally charged. But what happens if you rub the amber and the cloth together? Well, what happens is some of the electrons from the cloth get stripped away and deposited on the amber. So once you remove the cloth, there's an excess of electrons on the amber and an excess of protons remaining on the cloth. So you've created a separation of charge via rubbing, via contact between these two objects. It's important to point out that the total amount of electric charge is conserved. Charge is a property of matter, and it can't be created or destroyed. It can just move around from one place to another. So 2 electrons moved from cloth to amber, leaving behind 2 excess protons on the cloth. It's important to point out that when you're dealing with materials that are in the solid state, like in this example here, the chunk of amber and the cloth, the redistribution of charge always involves moving electrons. And why do you think that's so? It boils down to the fact that the protons are bound up in the nuclei of the atoms making up these materials, and they're not free to move around. However, the electrons, which are orbiting the nuclei, are somewhat free to move around from one atom to another, and so they're the ones that carry the charge from one object to another. This isn't true in the liquid state or the aqueous state, which exists inside of our cells. Inside of our cells, charges are redistributed all the time, and this charge can be negative charge carried by negative ions or positive charge carried by positive ions that are suspended in solution, aqueous solution. But in the solid state, charge moving from one object to the other is always electrons moving from one object to another. The other way that you can charge an object is called charging via induction, and that's illustrated in the right-hand side figure in this slide. So here we're starting out with two conducting spheres, metal spheres, and they're neutrally charged. And then what you do is, if the spheres are touching right here, charge can migrate from one sphere to the other because they're conductors. And then if you bring a positively charged object near one of the spheres, what happens is that positive charge attracts electrons. So electrons migrate over to the sphere on the left. And at that moment, if you separate the spheres so they no longer are touching and can no longer conduct electrons from one side to the other, and then take away this external positive charge, what you've ended up with is a situation where you've achieved the separation of charge. There's excess electrons on the left sphere and excess protons on the right sphere. So charging via induction involves using the attraction or repulsive nature of the electric force to redistribute charge on objects without actually touching the objects that are being charged. So quantitatively, we need a law that we can use in order to calculate the strength of an electric force between two static charges. This electrostatic force, or Coulombic force, is described by a force law called Coulomb's law. And it looks like this. The magnitude of the force between two, let's call them point charges, which in this picture are illustrated by Q1 and Q2, is equal to a constant K multiplied by the magnitude of charge 1, Q1, multiplied by the magnitude of Q2, charge 2, Q2, divided by the distance between the charges squared. So there's a lot of similarities between this Coulombic force and gravity in that it's a inverse square law, which means the strength of the force decreases proportional to 1 over the distance between the charges squared. Inverse square law. Now, unlike gravity, which is always an attractive forces between masses, this Coulombic force can be repulsive if the two charges Q1 and Q2 are both the same, either both negative or both positive, or it can be attractive if one is negative and the other is positive. So rely on a picture, as is shown here in A and B, to determine the direction of the force. Rely on this equation to determine the magnitude of the force. Another thing to notice is that this force law is consistent with Newton's third law. If we think of F12 as the magnitude of the force on 1 due to 2, and F21 as the magnitude of the force on Q2 due to Q1, Newton's third law says that those two forces are equal in magnitude but opposite in direction. And that's consistent with this equation, because if you look at the situation from the perspective of Q1 versus the perspective of Q2, all that does is reverse the order of Q1 and Q2 in the equation, but you're still multiplying them together and you still get the same number. So the magnitude of the force on Q1 due to Q2 is the same as the magnitude of the force on Q2 due to Q1. In the SI system of units and measurements, Q, electric charges, have units of coulombs, and 1 coulomb is a tremendous amount of charge. So in most situations, most problem-solving situations, you'll be dealing with fractions of coulombs, microcoulombs or nanocoulombs of charge. K, the electric constant K in this equation, is a very big number. It's 8.99 times 10 to the 9th Newton meters squared divided by coulombs squared. So K being very large means that even for relatively small charges, small Qs, you can have tremendous forces. The electrostatic force, the electric force, is a much, much stronger force than the gravitational force, for example, everything else being equal. I'll talk a little bit more about this in a few slides. Another way that we can study or learn about the way that electric charges influence other charges that are in their neighborhood is to use a construct referred to as electric fields. And electric fields are defined as the ratio of the electric force that's exerted on a test charge put in the vicinity of a charge of interest divided by the magnitude of that test charge. Well, what the heck does that mean? Well, let's consider an example. So in the picture up here, I've drawn a test charge, which for now, just think of it as a tiny charge that doesn't influence any neighboring charges, but can sense or feel and be influenced by the charges that surround it. So I've called it little q. All right, so Coulomb's law says that the magnitude of the force on that test charge little q is equal to k times little q times big Q divided by the distance between the charges r squared. So the strength of the electric field at the point where Q resides in space is equal to the magnitude of that force divided by little q itself, which works out to be E, which is the symbol we'll use to represent electric field, is equal to K times big Q divided by r squared. So in other words, the strength of the electric field anywhere in the vicinity of this K, or this Q, can be calculated using this formula, as long as you know how far away that point is from Q. So you could calculate the strength of the field here, the strength of the field here, the strength of the field here, and the strength of the field here, etc. So every point in space has an electric field that's being caused by this charge big Q, and you can calculate how strong the field is at every point in space using this equation, which depends on how big Q is and also how far away the points in space are from Q itself, squared. So for a point charge, we have an equation, E equals K Q over R squared, to determine the magnitude of the electric field at any point in space. But the electric field is also a vector quantity, which means at every point in space, the electric field has a direction indicated by the arrows in this picture. So the electric field is referred to as a vector field because the electric field exists everywhere in space, and everywhere in space, there's a magnitude of that field and also a direction of that field. So what direction does the electric field point? Well, we have a convention to help us out. And the convention is the electric field points, at any point in space, the electric field points in the direction that a positive test charge would move if it was placed at that point in space. So, for example, if I were to place a positive test charge right here relative to big Q, that positive charge, because big Q is also positive, would be repelled, and it would be pushed in this direction. Therefore, the electric field at that point in space points in the same direction. Instead of drawing little vectors at every point in space surrounding a charge to represent the vector field, which is the electric field, we have another technique, which is called drawing electric field lines. Electric field lines are not vectors, but they do indicate the direction a positive charge would move if it was subjected to the field. So the electric field lines for this big Q, which is a positive charge, is demonstrated over here in panel B. So the electric field lines point radially outward because that's the direction a positive charge would be pushed if it was placed anywhere in that field. So the way you would draw electric field lines is by thinking about the vector field and drawing lines that are tangent to the vectors represent the electric field at every point in space. So in this case, the tangent lines, because the fields point radially outward, also point radially outward. Let's look at some other examples. Down here, we have a picture of what the electric field looks like between what's referred to as parallel plate capacitor. One plate is positively charged and the other plate is negatively charged. So in between the plates, the electric field is relatively uniform and it points downward. Why? Because that's the direction a positive charge would move if it was subjected to this field. It would be repelled from the positive plate and attracted to the negative plate. Over here we have a distribution of charge referred to as a dipole, where we have a positive point charge and a negative point charge. And the electric field lines, if you drew the vector field surrounding these point charges and then connected the little arrows for the vector direction of the electric field at every point in space, what you'd find is lines that kind of curve around and connect from positive to negative, like so. Okay, so again, the electric field lines at any point in space, they point in the direction a positive charge would move if it was subjected to that field. So if I put a positive test charge right here, it would move in this direction. And that reflects the fact that it's simultaneously being repelled by the positive charge and attracted to the negative charge. And the net effect of that is to move in the direction of the field lines. So let me summarize. Electric field lines always point in the direction a positive charge would move if it was subjected to that electric field. And the way you construct electric field lines is by drawing lines that are tangent to the electric field vectors at every point in space. So one of the consequences of these rules is that electric field lines, if you have a distribution of charge like you have down here in this dipole, down here, then the electric field lines will always start on positive charges and end on negative charges. Another thing you can determine from electric fields is how strong the electric field is at different points in space, at least qualitatively. And the way you do that is by looking at how densely packed the field lines are. So for example, if you look at the dipole picture down here again, we can tell that the field is much stronger near the negative and positive charge than it is further away, because the field lines are much closer spaced near the charges than they are far away. So how close the field lines are to adjacent field lines communicates, at least qualitatively, how strong the field is at that point in space. So let's take a closer look at the electrostatic force and compare it to the gravitational force. So I've written the equations for the electrostatic force, F equals K, Q1, Q2 over R squared, and the gravitational force between two masses, M1 and M2, F equals big G, M1, M2 over R squared. I've written both of these equations on the slide. And so both of these equations look very similar. Both of these equations are inverse square laws. Both of these forces get smaller as the distance between the charges or masses gets bigger. And both of these equations involve some physical constant, which is a property of our universe. The electrostatic force has the electric constant K, which is a very big number. On the other hand, gravity has the universal gravitational constant, big G, which is a very small number. So this means if you have an equal portion of charge, 1 coulomb of charge attracted to another coulomb of charge, versus 1 kilogram of mass attracted to another kilogram of mass. And in both situations, the distances between the charges, or the masses, are equal. So everything else being equal, the electrostatic force is going to be much, much stronger than the gravitational force. But in a cosmic scale, in a galactic scale, it's the gravitational force which determines the dynamics of how planets move, how stars move, how galaxies rotate. And the reason is because there's only one flavor of mass, as far as we know, in our galaxy, and there's 2 flavors of charge. So in most situations, the amount of positive charge is balanced by the amount of negative charge. So the electrostatic force is 0, especially on galactic scales. And this is important because if it weren't for the fact that negative and positive charge were roughly balanced in most objects that we see in the world around us, then those objects would not be able to exist. They would be ripped apart by the strength of the electrostatic force. So electric forces and electric fields, again, are vector quantities. F's forces are vectors, E's electric fields are vectors. So if you have a situation like what's pictured here, where you have 2 charges, Q1 and Q2, and you want to know what the net electric field is at this point in space, labeled O, then what you would do is you would calculate how strong the electric field is due to charge 2, and how strong the electric field is due to charge 1, take their directions into account, and do a vector sum to figure out the total electric field between these two charges. We'll do examples of vector addition in class because it's probably been a while since you've done this. It's been at least since last semester, perhaps with momentum or forces. And adding vector quantities involves using trigonometry, using sines, cosines, etc., and also the Pythagorean theorem. So to finish up this lesson, I want to talk a little bit about conductors. Conductors are materials, at least in the solid state, that because of their atomic structure, have electrons that are relatively free to move around. And for this reason, if you charge up a conductor, the charge that you deposit on that conductor is going to want to get as far away from other free charges as possible. So for example, if you have the circular conductor, a spherical conductor like over here, and you deposit positive charge on that sphere, the positive charge is going to migrate to the surface. And it does that because it wants to get away, as far away as possible from the other positive charges that are nearby. And the net effect of this is that if you have a conductor, inside the conductor, the electric field is going to be 0 because you have this charge that's spread out, and inside it cancels out to give you an electric field of 0. And so an important application of this is something called a Faraday cage, and I'll show you a video of a Faraday cage in class. Another property of conductors is that when they're not uniformly shaped, like this cone over here, the electric charge tends to concentrate at places where there's sharp angles. So if you have a point, a conductor that comes to a point, and you charge it, a lot of the charge gets concentrated near the point, and this gives rise to very large electric fields in the vicinity of those sharp points. And this can cause, this is actually one of the properties of a lightning rod that makes it useful for dissipating charge buildup on objects, and via a process called coronal discharge. And I'll show you a video illustrating coronal discharge in class as well. Finally, let's say something about lightning. Under normal situations, there tends to be a charge separation between the ground on the Earth and the atmosphere and the clouds. And under certain situations, that charge buildup can become so great, the electric field between the Earth and the sky can become so strong that the air that exists between these buildups of charge, which is an insulator under normal situations, actually breaks down and ionizes and becomes a conductor. And for a brief moment in time, there's a channel of ionized air through which this charge can migrate. And that gives rise to a lightning strike. So this is referred to as, the air is referred to as a dielectric, because it is an insulator that separates two areas where charge is building up. And when the charge separation becomes so extreme, the electric field between the Earth and the sky becomes so strong that the dielectric breaks down and ionizes, you get a lightning strike. So this is called dielectric breakdown. All right, so this concludes our lesson on electric charges and fields. In class, we'll do some problem solving to demonstrate adding vectors, adding force vectors, adding electric field vectors, and continue our discussion on concepts.